Today we are continuing our work with solving these equations that are both either exponential or logarithmic. These first four examples are going to be very similar to what we saw in the previous day of notes. They really get different down here in 5 through 9, so those are where we're kind of looking at new patterns or new formats, but the method is essentially the same. What we've been doing is we've either been trying to make sure the bases are the same to apply the one-to-one property, or if we can't make the bases the same because we only have a logarithm on one side, we're going to convert it into the other format. We would convert a logarithm into an exponential or vice versa. So what we're adding new here is this. We have to check for extraneous solutions only when we're solving logarithmics, and that's because of the domain restriction. Because the domain of a logarithmic function generally does not include all real numbers, you should be sure to check that. So we'll talk about this. So let's see, why is this? So I'm going back to a previous example on a previous lesson when we were talking about this briefly. We were saying things like, I'm looking at example 9 right down here. If you're taking the logarithm of a negative input, that's simply not possible. If it's positive, we have an output there. You can see there's a point plotted, input, output. But on the negative input side, there's no graph at all, right? So that's outside the domain. The domain is only from 0 to infinity. I don't have a domain that includes the negative inputs. So if I work out my solution and I have a negative result, I need to test it. I'm going to plug it back in to see if I really am taking the logarithm of something that is positive or something that is negative. So that's what we're adding to today. So let's start off with number 1. This is our base. So let's convert that to exponential form. There's your base, there's your exponent. So it's e squared. E squared equals 3x. Again, we'll use our calculator and round to 3 decimal places. So 7.389. And then divide away the 3. So we're losing some accuracy here as we're rounding multiple times throughout the process, but this is what we'll do, right? So this is positive, so if we were to take this and plug it back in, you'd be multiplying by a positive 3. So you're taking the logarithm of something that's positive. That's good. Here's how you would check it more formally. You would take that as your input and plug it back in. We want to know, does the natural log of 3 times the 2.463. I'm showing it this way. We normally don't use the x for the multiplication symbol, right? But in terms of typing it in your calculator, make sure you have all of that in one large set of parentheses, because we want to know, will that equal 2? That's the question. So we type that in and we get 1.9999 and so on. So you can see it's really close to 2, and that's because of the rounding that we did on the previous steps. So yeah, it's essentially 2, it checks out. So that's how you check it formally, but what we will do is we'll just mentally take that result, plug it back in, and just ask ourselves, are we taking the logarithm of something positive or negative? If it's negative, we throw out that answer. Here's number 2, we have a logarithm on each side. The bases are the same, so we're using this one-to-one property. That means this value on the left of which we're taking the logarithm equals this value on the right. Okay, subtracting x from both sides, we have a 4x. Adding 1 to both sides, we have an 8, so x equals 2. So let's do that mental check. I have a positive 2, plug that back in for x. You're multiplying it by a positive 5. So it's still positive, even if you subtract 1, it's still positive, so that checks out. You have to check in each place. Take the 2, plug it in, add 7, that's a positive 9. That checks out, so we're doing fine. Here's number 3, natural log of the root x plus 5 equals 2. Again, there's your base. So that's e to the power of 2. So e squared equals the root x plus 5. Right? We changed it to exponential form. Again, we'll get this decimal value, 7.389. And then to eliminate the radical, we'll square both sides. So 54.597, and then subtract 5. So 49.597, right? So that's a very large positive value. If you plug it back in, you add 5, it's still positive. You take the square root of it, it's still positive. So yes, that checks out. Here's number 4. Once again, we have a logarithm on one side, so we'll convert that to exponential form. There's your base, there's your exponent of 8, so e to the 8th. E to the 8th equals 3x plus 4. We'll have a very large decimal value here, 2,980.958. And then we'll subtract the 4 from both sides. And then we'll divide away the 3. Right, so that's all calculator work on the left-hand side there. We have a positive result, so if you plug that back in, you're multiplying by something that's positive, you're adding 4, so it's still positive, so that checks out. So let's look at some variations. These are different situations or slight changes that might look like we haven't seen them before, but we're still using the same method. So take a look at number 5. Here we have the log of base x. That's different. Our variable is the base itself of the value 12 minus x equals 2. But don't let that stop you. We can still turn this into exponential form. There's your base of x, there's your exponent of 2. So x squared equals 12 minus x. What that means is you have a quadratic. So we're going to solve this the way we solve quadratics. Bring all the terms to the same side. So I'm moving them to the left. There's your trinomial. There's your exponent of 2, there's your exponent of 1, there's your constant term. That's the quadratic pattern. So we could use quadratic formula, we could complete the square, we can also factor. And that's the way to go here. It's a little faster. All right, so factors of negative 12 that add up to a positive 1. We want positive 4 and negative 3. Right? They multiply to a negative 12, but when you add them up, they add up to a positive 1. Separate your factors. So either x plus 4 equals 0 or x minus 3 equals 0. So we have 2 results. Or do we? We still have to check for extraneous solutions. If I have a negative result, that's a red flag. Plug that back in. Now when you plug it in here, that would be 12 take away negative 4. That's a positive 16. So that appears to be positive. But if you take the negative 4 and you drop it in for the base, log of a negative base, no, we can't do that either. And so that's where it fails us. So that's extraneous. We throw it out. And our only solution is 3. Now take a look at what we just wrote here on this line. That's going to apply to what we're about to see on number 6. So notice you have 3 terms right here, and you have this descending pattern of power of 2, power of 1, and then there's your constant term, right? That's the quadratic pattern. Now look at number 6. There's your power of 2. There's your power of 1. And there's your constant term. Do you see that same sequence? This is really a quadratic. It looks misleading because you have the e. So we're not used to seeing e's. We're used to seeing the x's in our quadratic pattern. And we have this also variable of x in there. So it's e to the power of 2x and e to the power of 1x. That might throw us off, but notice what you're looking at is the descending exponent. So you have a 2 and then a 1 and then a constant term. So 2x, 1x, and a constant term. That's the quadratic pattern, which means we can solve it with factoring. You want the base of v in front, right? Because you have to multiply these together to get the e to the power of 2x. So the question is, what exponent do I need? E to the power of what? Times e to the power of what gives me that e to the power of 2x. Well, there's 2 x's, and you have to have x's on both of them to have an x on there anyway. So what happens when you multiply these together? You multiply the bases, and you add the exponent. So 1x plus 1x is the 2x that you see. So that checks out. The constant term is 6, so we want factors that multiply to 6 but add up to a negative 5. So that's a negative 3 and a negative 2. Separate your factors, so each is set equal to 0. That means we'll get 2 answers. Now that's an exponential, of course. You have e to the power of x, and we're going to turn it into a logarithm, but not quite yet. You have to isolate that base first, so that means move the constant term to the other side. So e to the x equals 3. That's the format that you need. Now we can turn this into a logarithm. There's your base of e. There's the power of, or that's the number of which you're going to take the logarithm, right? So natural log of 3 equals the exponent So that's your answer in its exact form. If you turn that into a decimal value, 1.099. Same idea over here. We have e to the x minus 2. We want to get the e to the x by itself. Move the constant term to the other side. Turn that into a logarithm. Natural logarithm of 2 equals the exponent. That's your exact answer, and our decimal value is 0.693. Both of them are positives, but I don't have to check for extraneous solutions because this is an exponential pattern. Only with logarithms do you have to check to see if you have an extraneous solution. Numbers 7 and 8 are similar in their first step. You can see the note right there. You have to condense. If you have multiple logarithms on the same side, you can't work with that. You can only have one logarithm per side. So that's why we're going to condense those down into a single logarithm. So log base 4 of, and then all of these are being multiplied together. You have an x. No, they're not. What am I talking about? That's a minus sign. We will have a fraction. So it's log base 4 of a fraction. What comes in front of that subtraction sign is the x plus 1. What comes in back of that subtraction sign, that sinks down to the denominator. Okay, that's a single logarithm, which means we can now convert it into an exponential form. There's your base of 4. There's the exponent of 1. So it's 4 to the power of 1 equals the x plus 1 over x. Well, set that up as a proportion. Create that 4 with a denominator of 1. Now you can cross multiply. So here you have on this diagonal 4 times x, and on the other diagonal it's 1 times the x plus 1. So that means you'll have 3x equals 1, and then x equals 1/3. Now this is a logarithm, so we do have to check for extraneous solutions. So take that positive 1/3, drop it in. If you add 1, it's still positive. What about over here? If you drop it in here, it's still positive. So it checks out. We're good. Number 8. This is the one with the plus sign. This is what I think I was thinking about here. We want to condense that down again, so we have a single logarithm per side. We already have one logarithm on the right, but we have 2 on the left, so let's condense that down. Natural log of, okay, there's my multiplication sign, because we're multiplying that x times the x squared minus 8. Right, there's my grouping symbols. We want to take the natural logarithm of all of that. That is equal to the natural logarithm of 8x. Now notice you have the same base on each side. You have one term on the left, one term on the right. In terms of, you've got one logarithm on each side. Those are matching bases, aren't they? So this is our one-to-one property. The values of which you're taking the logarithms must be set equal to each other. All right, we can divide both sides by x, so those x's cancel out. So x squared minus 8 equals 8. X squared equals 16. We're taking the square root of both sides. Don't forget your plus or minus. You have plus or minus 4. However, I have to watch out for those negatives. So let's check that negative 4. I'm going to take that negative 4, and if I plug it in here, it fails. I cannot take the natural logarithm of a negative value. So the answer is not plus or minus 4. The answer is only positive 4. Here's our last example, number 9. So again, we're showing you problems that don't look quite the same as the others, but you'll see they have a very similar technique to what we've seen either yesterday or today. So check out this problem. That's quite a base. We have 1 plus 0.08 over 12, all of that raised to the power of 12 times t. I don't know if you recognize that, but that actually comes from our financial formulas. When we're looking at compound interest, normally you would have a number here, that would be your principal. Then you have 1 plus, that's 8% over 12 compoundings, raised to the power of 12 compoundings times the time in years. So that's essentially where it comes from. But let's see if we can use our methods to solve for the time. Okay. What we're going to do here is, first of all, let's just simplify that base a little bit. We can turn that into a decimal value. 1 plus a very small number means we're going to have a lot of decimal places. Normally we might round to just 3, but we're going a bit farther here because it's such a small value. It's a very small increment. We want to make sure we can see that difference as we work this out. Okay, so I just turned that fraction into this base, but it's still my exponential form. There's the base, there's the exponent. I can't make the bases the same. I can't use the one-to-one property. So let's turn it into a logarithm with this base. Log with the base of 1.00667 of 2 equals the exponent, 12t. So again, our goal is to solve for t. And we know we'll have to divide away the 12 at some point, but not yet. What do we do on this side? How do we turn that into a value? This is where the change of base formula comes into play. So log of 2 is on the numerator, and on the bottom you have log of. And what used to be the base is not the base anymore, it's just the log of 1.00667. So this is the common base. You use that on your calculator, and it's pre-programmed to have a base of 10. Right, so that'll give you a decimal value. So all of that equals the right side of 12t. So my calculator tells me the change of base gives me a result of 104.266. That equals the 12t. And then we'll divide both sides by the 12 to get a result of 8.689. So there's the time in years.